I'm pleased to be able to come and share a bit of a perspective from space, from my career at NASA. I'm actually from here in the Tri-Cities, and went to work at NASA, but then came back in order to help with family here. So I'm glad to be back in the Tri-Cities, and glad to be able to talk about what I did at NASA while here in this great place. I was gratified that Jim started with Psalm 19. It's always been a favorite of mine. And as you're aware, Psalm 19 continues to talk about the creation, but then halfway through it switches and talks about the Word, right? It talks about how the Word is precious, right? Sweeter, more to be desired than honey, or the honeycomb. The law of the Lord is perfect, converting the soul. The testimony of the Lord is pure, making wise the simple, and so on. And I think it's Psalm 19 that gives rise to this idea that there's the book of the world and the book of the Word, and that both of these together comprise a revelation from the Lord through whom we get to know Him better, through which we get to know Him better. And so I hope to return to that at the end of my talk, because what the two speakers on the video brought up, McGrath and Lennox, concerning non-overlapping magisteria, is something that I've been thinking about in the context of this talk and the discussions we've had. So we'll talk about that towards the end. Well, let me see if I can make this guy go here. All right, so I want to talk a few things about what NASA does. My friends at NASA that work aeronautics have to remind me all the time that the first A in NASA is aeronautics, National Aeronautics and Space Administration. This is the one area at NASA that I did not have an opportunity to work in, so I won't talk about that. But I wanted to give a shout out to my aero friends, because as they like to tell me, NASA is with you when you fly. A lot of what we do to enable safe flight comes out of the work that NASA and its predecessor organization did over the decades. NASA also explores the Earth with the vantage point of space. I got to work in that realm for about 10 years or so. So if you ever want to hear about, we heard an excellent talk a few weeks ago from Steve Gahn about climate change. That sits in a broader context of Earth system science or system change. And so if you'd ever like to hear about that, we'll talk about that on another occasion. What I do want to talk about tonight are the two realms of human spaceflight, and then also, from the perspective of the solar system. This is a little itchy on this trigger finger here, so we'll see if we can get through it. I want to talk a little bit about why I got interested in this world in the first place. Why would somebody from the deserts of Eastern Washington be interested in the physics of the universe and the exploration of space? So I wanted to share a couple of photographs that illustrate that perspective, that interest. This is the 1927 New York Yankees, which is arguably the best baseball team ever assembled. Included the 6 members of Murderers Row, plus 3 on the pitching staff who won 18 games or more. And that was going on in 1927, also the year of my father's birth. But while this was going on in America in 1927, there was another gathering of like luminaries in Europe. This is the 1927 Solvay Conference on physics. This is the all-star team. This is the 27 Yankees of physics. Everybody is here. Madame Curie is here. Albert Einstein is here. Louis de Broglie is there. Max Planck, Max Born, Heisenberg, Wolfgang Pauli, Arthur Compton, Niels Bohr. Everybody was anybody in physics, and this was the revolutionary period in physics, the understanding the relativity theory and quantum mechanics, and then what was called the new physics. Everybody was here, and I was always fascinated by this period in the history of science. Understand why these folks? What has there ever been a gathering of people like this? It's these guys. It's the 27 Yankees. It's the founding fathers. It's the apostles. Right. Every now and again, there's an assemblage of remarkable people, and great things happen as a result. And this was one of those eras. And these were the folks that were tackling questions that I was just fascinated by, even as I could not really understand the questions themselves. Why is there such a thing as Planck's constant? Why should there be an irreducible minimum, a quantum of energy, if you will? Why? Why is that? Why does E equals mc squared? What sense does that make? It looks so idiot simple. Why should it be true? Why is the speed of light the balancing term between energy and mass? You know, it's a fascinating thought. Why does Bohr's model of the atom with a tiny nucleus surrounded at relatively great distance by an orbit of electrons, why does that kind of look like a solar system with electrons in distant orbits around that nucleus? I don't know. And why, at the bottom of it all, does there just seem to be probability distributions of energy? These are questions that I just thought, why? Why does this make any sense? Is there somebody who thinks this stuff up? These are things I wanted to know. Also, when I was a child, there was this cast of characters, right? And this, if you were, as many of you were around during that time frame, this was an interesting phenomenon. One of the things that made it interesting was this aired in late 1966, early 1967, ran for 3 years, during some very intense years of the Cold War. And while many of us were wondering, you know, is the politics of mutually assured destruction going to wind up that we're all destroyed? And while that was all going on, and the nuclear triad, right, was running full throttle, right, in the air, under the ocean, in land-based missile silos, while all that was going on, this was telling us that, you know what, there's a future beyond, potentially. There's a future beyond the fear we're experiencing. And so I was fascinated by this construct for that reason. And the fact that there could be, in fact, multiple races, multiple nationalities working together towards a common goal with a common understanding. I didn't know it at the time because I wasn't a Christian, at the time. But I've since been enamored with the vision presented in the Revelation in chapter 5 of people from every tribe, tongue, nation gathered together around the throne to worship the Lamb. And this was sort of a proto, if you will, image of that notion, which I later became so fascinated by. But then what happened in that time frame, of course, was Sputnik, the launch of Sputnik, which was a huge, earth-shattering event, particularly on the American psyche, knowing that the Ruskies were in space and they were potentially watching us from on high, that they could overfly our country at will. Oh heavens! Okay, I'm so sorry. Yeah, it's a little bit itchy. Thank you. But Sputnik was a huge, momentous occasion and event. It actually turned out to be good for the U.S. One reason being that it allowed us to not have the argument with the Russians about overflight rights because they did it first. And so because they did that, we could launch satellites with impunity and overfly any country we wanted to. And there was no question that it had to be aired in the UN because of that, because the Russians had already done it. So, and then of course, Kennedy's speech. This is the picture before the joint session of Congress where he announced that it would be our goal to launch a man, send him to the surface of the moon and return him safely to the Earth within a decade, which was a remarkable announcement and a remarkable accomplishment. And then, of course, we went on to proceed with the Apollo program. This is a very itchy mechanism. The Earthrise image, you've all seen that Bill Anders took. Actually, when he took the picture, it was oriented 90 degrees the other way with the surface of the moon on the right because they were making an essentially equatorial pass around the moon and wanted to have the picture oriented that way because of the geometry of the approach for the future flights. But this is the way it's often viewed by the rest of the world. Again, an iconic picture, memorialized in a stamp. The stamp reads, "In the beginning, God," because if you recall, during that mission, the astronauts read the first 11 verses of Genesis 1 because they felt that was it was appropriate, but it also was something that Christians, Jews, and Muslims could all agree on. Of course, you may remember the name Madalyn Murray O'Hair, who was made herself famous as an atheist and sued to have the Bible removed from public schools, that sort of thing. She sued NASA over this reading of the text from Genesis. And I think they went all the way to Supreme Court, and I think they decided that because it was read in space, it was out of their jurisdiction. Of course, the Apollo did proceed. There's the famous photograph of Buzz Aldrin on the surface of the moon, and you can see reflected in his visor Neil Armstrong, who's taking the picture, as well as lunar module in the background. Buzz Aldrin, his name actually was Edwin, but his name actually now is Buzz. He actually had it legally changed. He's kind of a crazy guy. He's still active in the trying to influence space policy. But Apollo 11 and subsequent missions, Apollo was followed by the Space Shuttle program, which flew 135 missions and demonstrated the idea of reusability in spaceflight, that we could actually not waste all the hardware we sent into space, but actually refly it, which was a big deal. You see there at the lower right, the first two gentlemen were from the first shuttle flight, Young and Crippen, and then the four to their left were from the last mission, 135. Space Shuttle accomplished a great many things, including the deployment of the Hubble Space Telescope, the Galileo probe to Jupiter, the Cassini mission to Saturn, the Space Lab in the Shuttle Bay, which was the first laboratory to do research on materials and their properties and how they behaved in microgravity. And then, of course, we had a couple of catastrophic failures, including the loss of the crew of the Challenger, which occurred about 6 months after I went to work for NASA. It was really a momentous and traumatic event for the agency, but taught us some hard lessons about human spaceflight. But what the shuttle principally accomplished was the building and the assembly of the International Space Station. And so my daughter, who's sitting back there at 18 years old, has never lived in a world where there weren't people living and working in space on the International Space Station. It's called that because the U.S. did it in partnership with Europe and Japan and Canada. And then halfway through, the formulation of the project, the Cold War ended and we invited the Russians into the program. Jim was telling me earlier about work with the Russians and how we employed some of their scientists in joint projects. One of the rationales for bringing them into the program was so that Russian scientists and engineers could turn their attention from Cold War weapons pursuits to peaceful exploration of space with us, as opposed to other things that high bidders might want them to do. But in any case, the Russians are very they're wonderful as space engineers, and they've been a very important and vital part of the program. Just to connect the two worlds I'm going to talk about, space and space exploration and physics. Boy, this is really an itchy guy here. The coldest place in the universe is now actually a locker on the International Space Station. The Cold Atom Laboratory is essentially an experiment designed actually to, I mentioned Louis de Broglie, who was one of those sitting in the 1927 Solvay conference. A de Broglie wave essentially is if you think about photons as exhibiting both waves of exhibit properties of waves and of particles. It turns out that any particle of matter will do that if you could isolate it and slow it down and take enough energy out of it. Then a atom, for example, of potassium will begin to smear and become essentially an energy probability distribution curve. And that was demonstrated in laboratories on the Earth, where they could get a hang time, if you will, a wave to appear for a total of about a second. And there were 3 Nobel Prizes, or a Nobel Prize to 3 people given to effect that experiment. We took that experiment with their help to space because gravity is is a form of energy, right? And it operates on a particle, and it interferes with that energy extraction and smearing process. And so we discovered that in the zero gravity environment of space, we could get a hang time of about 5 seconds, which if you're a particle physicist is an eternity. So again, a place where human spaceflight and basic physics intersect. You may recognize these two gentlemen. This is Mark and Scott Kelly, both of whom were NASA astronauts. Mark Kelly, you may remember, was married to Representative Gabrielle Giffords, who was a victim of an assassination attempt. He then, after his last flight, retired from the astronaut corps to help care for his wife and help her recover, which he has done remarkably well at. But his brother Scott continued with the human spaceflight program, and Scott was selected along with Mikhail Kornienko from Russia to fly a 1-year mission to the space station. We've generally been flying astronauts from 90 to 180 days. But if we're going to fly to Mars, we've got to be able to know about human behavior and health and performance in more longer duration space missions. And so we thought, well, let's fly these guys for a year, have them on the space station for a year, and see how that works. And then Scott Kelly thought, well, wait a minute, there's an opportunity here for additional research. I've got a twin brother with identical genome, identical DNA on the Earth. Why don't we run a series of experiments, a series of test protocols, a series of samples that will allow us to understand the impacts of human spaceflight, of microgravity environment on the DNA of two identical samples. And so we ran that test, and just 2 months ago, Science Magazine dedicated an issue to the results of that work. And while we observed the Scott's gene expression levels changing during the course of his year-long mission, we saw that in the aftermath, within 6 months of his being back, a lot of those effects went away. We also saw that, for example, a flu shot given to Mark on the Earth and to Scott in space had equal effectivity, had equal, they worked exactly the same way, which was an interesting result with respect to the prospects for medical care and long-duration spaceflight, and so on. And so there's a whole series of articles on that, which is going to inspire some future missions to employ this kind of a protocol. And so we continue then to select astronauts to fly into space in preparation for future missions to the Moon and Mars, including from this class in 2017, Richland's own Kyla Barron from the class of 2006. So we're on the way to explore with humans the Moon and Mars. If you've been around NASA or have followed it in the news from afar, you know that there's a constant ongoing back and forth debate between what I call the Martians and the lunatics. In other words, should our next destination be the Moon or should it be Mars? There are those who say you want to go back to the Moon first because Mars is a long way away. You want to be able to test operational techniques, assure you can survive on another planetary body for a long period of time before venturing to Mars. Others would say, no, not really, because the Martian environment is so different than the Moon that what you learn on the Moon isn't going to help you all that much. The problems you really ought to be focusing on are, for example, entry, descent, and landing, and then ascent from the Martian surface, which is a fundamentally different problem when you have an atmosphere versus when you don't. And so this argument goes back and forth, and it turns out that as a government agency would have it, as a government agency is victim to, it depends on who's the president and what party they're from. And so under the last administration, Mars was the focus. Under the current administration, the Moon is now the focus. And so my boss, who ran NASA's human spaceflight, continues to run NASA's human spaceflight program, he's a very cagey individual. And so he thought, while these guys are having this argument, beating each other over the head, let's work on the pieces of infrastructure we know we're going to need regardless of destination. And so his focus has been on the Space Launch System, which is represented by the three versions of the vehicle on the right, and the Orion crew capsule, which will be the first crew vehicle since Apollo to be able to travel beyond low Earth orbit. And both of those are well along in development and should be ready to fly in the next couple of years. This thing wants to advance without even touching the button. That what we'll do next is a outpost called Gateway, from which we will be able to access both the lunar surface and Mars in minimum energy trajectories. So the current administrator of NASA, Jim Bridenstine, is going to continue to push for the current administration's priorities, which is to get back to the moon first. That's where we're headed next. And so last month, NASA released a solicitation to tap American industry to develop a lunar descent and ascent vehicle. What's new about this is that in contrast to what we were doing 50 years ago at Apollo, is that there are now lots of players in the space game that are non-governmental entities, right? There's SpaceX, there's Blue Origin, there's Virgin Galactic. There's probably a dozen US-based companies that are developing spaceflight capability, spaceflight hardware. And so rather than the old days where we would put out an RFP and choose between Boeing and Lockheed to go build something. We can now enter into partnerships, innovative acquisition partnerships with these commercial firms where they're putting some skin in the game because they have exploration goals that they are invested in that are compatible, synergistic with ours. And so we now have a way to do space flight that is going to be faster and cheaper than former acquisition models. Meantime, we still have our sights fixed on Mars because it is an interesting place to go. I love this picture. While this is an artist's concept, the thing that's wonderful about it is that Mars has 2 moons, Phobos and Deimos. If you were standing like this person is on the surface of Phobos, that's how Mars would look to you. The relative sizes are accurate. So why Mars? This is actually an image taken from the Mars Reconnaissance Orbiter. It shows what appears to be a dry river stream with a delta in the center of the picture. And in fact, what we have discovered is that Mars once had considerable liquid water on its surface. This is a dry stream bed on Mars. It shows with a rock outcropping in the circle there that they've named Hota after a lake in northwest Canada, because that lake in northwest Canada, which is now dry, looks exactly like that stream bed, except that the coloration is different. But you can see the small rocks and gravel in the center that look like they're formed by sedimentary processes. And so it is supposed, theorized, that Mars at one time had considerable water resources on the surface. And the question is, what happened to it? Well, so we sent MAVEN, the Mars Atmospheric Volatility and Evolution Explorer, to Mars to understand, to try to understand the details of what happened. And what we think happened to Mars is that, for reasons that are unclear to us, its magnetic field in the past died out. Its magnetic core, and whether it's iron core continued or ceased to rotate or what have you, it no longer produces a strong magnetic field like Earth has. It's the magnetic field on Earth that holds our atmosphere in place and keeps the solar wind and solar storms from essentially driving it away. Mars was not so lucky. Mars' magnetic field failed, and its atmosphere over the years was blown away literally by the solar wind. And MAVEN documents that process. It actually watches the interaction of the solar wind against the remaining Martian atmosphere, and it documents the process of its erosion, if you will. But the result is that Mars still has considerable water resources. There is water we've demonstrated in the form of ice within a few inches of the surface over much of a very high percentage of the Martian surface, and that is accessible to us. We've actually seen through, for example, the landing of one of our Mars probes, that when we have cameras looking down, if you can imagine looking down from the descent, and the descent engine is firing, and it blows away the gravel, right, the dust that's there, and exposes the ice. And we know it's ice because not long after that thing's set down and we're looking at it, we can watch the ice sublimate away into the atmosphere. And so we've been able to demonstrate that. Nevertheless, what we've come to understand is the exploration of Mars is hard, right? In order to support a human presence on Mars, you need to be able to land 20 to 30 tons, right? Imagine trying to land safely 20 to 30 tons at a time on the Martian surface. You need to be able to operate for 800 to 1,000 days away from Earth in microgravity during transit, and then in the 1/3 gravity on Mars for the duration. You need to establish reliable communications when there's as much as a 44-minute two-way communication delay. And you need to be able to generate oxygen on the Martian surface, which I'm going to talk about in just a second. But the exploration of Mars is hard, and so our technology program is aimed at solving these problems. And so we have now the Curiosity rover on Mars. It's going to be joined soon by the Mars 2020 rover, which we haven't given a clever name yet. We usually let Curiosity was actually named by a student. We had an open competition, and the students wrote essays, and then we had a team of folks, including educators, selected from among those essays. We'll do the same or something similar for the 2020 rover. This is essentially the same design with a different instrument package. One of the instruments on there, you see at the center and the bottom, called MOXIE, is one that I was involved in selecting when in my last job at NASA. MOXIE is designed to ingest carbon dioxide from the Martian atmosphere. That's its principal constituent. Ingest that carbon dioxide, crack it into carbon and oxygen, and store the oxygen. The idea then is if that works, it behaves as hoped, as expected, that we could then scale up that experiment, drop one of these instruments on Mars while we're planning the next Mars, for the first human Mars mission, and essentially build up a store of O2 for use by the astronauts for both breathable air, but also for making their own rocket fuel for the return trip. Because you'd love not to have to take all that with you, because mass is at such a premium. So MOXIE is something we're kind of excited about. This is something else we want to carry on the. Can you fire that up from back there? This is actually a helicopter that we want to that our aeronautics friends at NASA are helping us develop so that we can fly this on the 2020 mission. It will arrive on the undercarriage of the Mars 2020 rover, and then be deployed from there. One of the ideas here is that it can then fly ahead of the rover, map the terrain, and then provide that guidance back to the rover. Because one of the things, if you follow Mars rovers today, they're very slow going because of the delay in transmission time. Because the scientists have to the operators have to assess the terrain ahead, go a little bit, assess the terrain ahead, and so on. The helicopter can communicate with the rover some advanced in situ guides. This is at the Jet Propulsion Laboratory in California. This is in a chamber that is filled with CO2 and at the Mars atmospheric pressure for the surface to test whether this thing can actually work. This test was conducted a few months ago, and we've convinced ourselves that, yeah, this can indeed work, and so we've added it to the Mars 2020 instrument package. Okay, we go back to the... So very interested in Mars because of what it enables in terms of habitability. But Mars is the only interesting body in the solar system. The moons of the giant planets are interesting as well. This is Europa. Europa, you can see the striated surface there. That essentially is are cracks in the covering, the surface of the ice surface, the covering of that is caused by the push and pull and thermal interaction with its host planet Jupiter. The Galileo mission that we sent to Jupiter made close passes by Europa, and what we've discovered is that under this cracked ice surface is a liquid ocean. And so we're going to send the Europa Clipper mission to fly by Europa several, probably 75 times if we can get it to last that long, to really do a detailed mapping of that Europan surface. And eventually we'd love to be able to fly and land a vehicle on the Europa surface that can then drill through the ice, drop down a little submarine that can robotically that could swim around and see what actually is there. So we're looking forward to being able to do that. They've tested it actually at some sites in Mexico with underground aquifers. Enceladus is another moon of Saturn that's interesting. We've seen from the Cassini spacecraft that Enceladus has essentially geysers that are spewing out water and other particles from an internal water source. The next mission to Saturn is going to actually try to fly through this plume to get a real look, an in situ look at its chemical constituents. Titan is the only other body in the solar system that has liquid flowing on the surface. And it has the equivalent of a hydrological cycle. It exhibits evaporation, it exhibits precipitation, it exhibits flow on the surface. The bad news is that it's not water, it's methane. And so, but still, it makes it a very intriguing, scientifically, very intriguing target. And so we actually have proposed by the person who was NASA's last chief scientist to drop a sailboat in one of these lakes and robotically tool it around and explore that aspect of the Titan surface. So lots of interesting places. And now we've discovered that there are planets elsewhere in the galaxy, planets that are termed extrasolar planets. In other words, they're not around our sun, they're around other stars. This is the Kepler mission. Kepler was designed to stare at a specific region in space, in the Cygnus field, to stare at it for multiple years, to stare at a population of about 10,000 stars, and see if it could detect transiting planets. The way it does it is it stares at a star. If a planet of sufficient size passes in front of that star, there is a reduction in the light coming from that star. And then when it passes around the other side, that light wave comes back up. And so through this technique, Kepler has found by itself over 3,000 such planets. And then there are 1,000 other ones from surface telescopes and other instruments. And we've mapped those. You can see size relative to the Earth and radius, and then its orbital period. And what we've seen are a lot of hot Jupiters, a lot of ocean worlds and ice giants like Neptune and Uranus, rocky planets roughly down to the size of the Earth, and then what's labeled frontier down below is we'd love to be able to detect rocky Earth-sized planets that have an orbital period similar to ours. In other words, they're sufficiently distant from their star that like Earth, water can exist in all three phases. That's what makes life possible on Earth. And so our goal is to be able to get to be able to detect planets of that nature. This is a cartoon, if you will, of the TRAPPIST system. I can't get it to hold on this picture. But what this shows, what this illustrates, is that we have discovered multi-planet solar systems. This is the TRAPPIST system. There are 6 planets in this system, all of which are either Earth-sized or up to twice as large as the Earth, and they're all rocky bodies. They're not gas giants and so on. And so to be able to find multi-planet solar systems is a pretty cool thing. And so it's led to some clever people to maybe, in an entrepreneurial sense, start a little exoplanet travel bureau. And it's kind of a clever way to catalog the data on these exoplanets, get some sense of document what their characteristics might be, and then where we're going next, we launched last year the TESS mission. So Kepler picked one region of space that was fairly far away and stared at it for 4 years. TESS, by contrast, is doing an all-sky survey, but of our near solar system neighborhood. And so for the 10,000 or 100,000 stars that are closest to us, it's going to survey all of those and try to do a census, if you will, of planets that are close enough to us such that future generations of telescopes can observe them directly. So that, and it's discovered its first Earth-sized planet and its first warmer sub-Neptune-sized planet, and they're just getting started. This is Hubble Space Telescope. It's become sort of an iconic friend to a lot of people interested in science and astronomy. Its discoveries are legion. Hubble itself was an interesting character. Hubble is widely considered to be the greatest of so far of American astronomers. It was Hubble who discovered, if you will, that the galaxies are receding from us, and therefore the universe is expanding. He was the first one to make those detailed measurements. He was also a multi-talented, colorful character. He played on the University of Chicago 1909 championship basketball team as a forward. And so John Grunsfeld, an astronaut who was involved in several of the Hubble repair missions out of the bay of the space shuttle, you can see the top of the Hubble sticking out of the window, through the window, out of the back of the shuttle flight deck. That's the Hubble basketball, which he borrowed as a University of Chicago alumnus. He was able to borrow that and fly it on this mission. Hubble highlights, I said, are legion. One of the things that Hubble allowed us to discern is that black holes are common in the galaxy, in the universe. This was the image you probably saw. You may have seen a month ago, the first image of a black hole, if I could say it that way. The black thing in the center is the black hole that you can't really see. What you're seeing around the ring around is just outside the event horizon, the pulse of X-rays that come off of a black hole as it ingests everything else around it. And then Chandra, another NASA space observatory, actually looks in the X-ray portion of the spectrum and allows you to see the X-ray context of that black hole. So space telescopes have allowed us to begin to understand the nature of the universe around us. This is COBE, the Cosmic Background Explorer. Back in 1990, it gave us the first picture of the cosmic microwave background. And that was important because if Edwin Hubble was correct, that the universe is expanding, galaxies are receding, if you project that backwards, there must have been an origin. If there was an origin, if there was a Big Bang, as Fred Hoyle named it, then it would leave residue. That residue would be the cosmic microwave background. And COBE was designed to measure, to detect that background. And it did so, and what you see in this seemingly random pattern of red and blues and colors is essentially the fact that there's a lumpiness, if you will, to that microwave background. The lumps represent the galaxies and everything else out there, including planets and ourselves. And so the early results from that cosmic microwave background were plotted on a graph of intensity, which was a proxy for temperature and wavelength. And what you see there is actually two curves. Right? There's one curve that is a theoretical observation if there was a Big Bang leaving a cosmic microwave background. The other curve is the actual observation data from COBE. As you can see, they perfectly match. When this result was presented, the entire astrophysics community present at the time stood up and applauded. And as a result, John Mather and William Smoot were awarded the Nobel Prize in Physics in 2006. John Mather works for NASA. He was the project scientist for COBE. This is that same cosmic microwave background now from a mission called WMAP, which was a next generation finer resolution detector than COBE had. So what you see is that same sort of pattern, but now in a much more finely grained detail. And so now we can begin to understand that era of the universe after the Big Bang and what did it look like. Well, it produced some kind of weird and amazing effects, of the nature of which we're still trying to discern. What you're seeing here on the left is a Hubble image of a galaxy cluster, and you can see that some of the galaxies are elongated and there's sort of bluish streaks surrounding them. That is the product of gravitational lensing, which comes from Einstein's general theory of relativity, which was proven by observations in the early 20th century of solar eclipses, and how the light from the stars, light from those distant stars, was being bent by our own sun before they reached our telescopes. What you're seeing is that same phenomenon that smears these galaxy shapes out. And so what astronomers have done is they've looked at all of this lensing data and then figured out mathematically what mass would have to be present in order to affect that gravimetric phenomenon. And so the bluish, on the right side, the bluish cloudy image is essentially the inferred presence of dark matter. We don't know what it is. Astronomers, when they don't know what something is, they refer to it as dark. It's dark energy, it's dark matter, it's a black hole, right? That's just their thing. But mathematically, at least, that's what a dark matter pattern looks like. And so what we've tried to do then with Hubble and WMAP and other space telescopes that we've flown is try to discern the history of the universe. We try to look at each of the wavelengths and of the eras to try and piece together a picture of the universe's history. I had an interview with a high school student one time, and I blew her mind with this statement because it blows my mind. To see far away is to see long ago. That's just the way the universe is. And so when we look at the most distant objects of the universe, we're seeing the first galaxy formation, the first star formation. Behind that, we look at the cosmic microwave background, which is that that blue-greenish thing just turned on its side from what I showed you earlier. And then what's theorized is this period of inflation, which I think Scott Chambers mentioned when he was here before. That rapid expansion in the very first seconds, even microseconds after the Big Bang, starting with quantum fluctuations that are associated with that Big Bang. And actually, I wish I'd taken a picture of the cover, but the National Academy of Sciences, under sponsorship of NASA, did a study, and it's called From Quarks to the Cosmos. And what it shows you, or what it tries to elucidate, is the connection between the very small subatomic particles, quarks, and gluons, all those things, and the unimaginably large, the nature of the universe itself. It turns out that there's a relationship, and that relationship was exhibited most strongly in the Big Bang itself and the immediate aftermath, including the inflation. And so we're trying to actually, one of the missions in NASA's Dock into the Future is an inflation probe that will study that very early picture of the universe, if we can make it work. But the odd part of this picture is off to the right, where you can see it's accelerated expansion. What astronomers had thought, even after the acceptance of the Big Bang theory, was that the universe's expansion would eventually slow, or at best it would just continue on via inertia. What observations from Hubble and other instruments have shown us is that in fact it's not true. What's actually happening is that that expansion is accelerating. We have no idea why, and so because we didn't, we had to create a term, dark energy, to try and explain to ourselves why that is. So you can think of dark matter as why galaxies and galaxy clusters can hold themselves together in the face of the rapid speeds at which they churn, and the answer appears to be some form of dark matter. The thing that it is causing the universe to continue to expand appears to be something called dark energy. We have actually no idea what it is, so we're going to try to figure it out. This guy on the left is the James Webb Space Telescope. It's going to be launching, we hope, in 2021. It's been a bear cat to try and build. It operates, it doesn't look like a telescope because it's looking in the infrared, so it doesn't look like a conventional telescope like the Hubble does. This is if you get a sense of proportion, this is the clean room at Goddard Space Flight Center where the primary mirror is being assembled, and then the people standing around there. So you can see this thing is quite large, and it's proven again to be a challenge to assemble. The biggest challenge being, as you can imagine, the calibration and the alignment of these mirrors and the instruments behind them, because they not only have to be aligned, they have to be calibrated, but they have to survive the vibrations of launch and come out the other side. And so we're hoping to continue to be able to get this thing to go, just like I'm trying to get this projector to go. I don't know if this is going to work or not. There's I don't know if you can make it go, Scott. There's if you tap on the picture, you should see a little animation. Oh, there you go. So what this is showing is the deployment or the placement of the orientation of James Webb in space. There's the Earth and the Moon and the Sun. James Webb is going to be at L2, the second Lagrange point, 1 million miles from the Earth. It needs to be out there to get away from the sun's light, and then you'll see the primary mirror is oriented, sort of pointed that way, and then to the left, that big surface area is essentially a 5-layer sun shield, because we're trying to shield the instruments both from the heat from the sun and the light from the sun, and it's going to operate at about 40 Kelvin. So that's a challenge to make happen. All right. So that's James Webb. I hope to launch that in 2021 on an Ariane 4 or Ariane 5 launch vehicle in partnership with Europe. What's next, because astronomers always think about the next thing, is called WFIRST, the Wide Field Infrared Space Telescope. It's really designed, optimized to understand the question, what is dark energy really? Is it a form of energy, or does general relativity itself need to be modified? Einstein thought his biggest mistake was the cosmological constant. Turns out that Einstein was so smart that even his mistakes were true. So we're trying to discern which is the case. Is there something called dark energy, the nature of which we don't understand, or does general relativity itself need to be modified? W first is going to help us figure that out. And just a little trade secret, W first was proposed by the National Academy of Sciences, and they force fit an acronym to W first because they wanted the U.S. to be first, because the Europeans were also interested in this question, and they're actively working on it. So if we get ours going first, well, we'll be ahead. So looking again farther ahead, we're looking at all the portions of the electromagnetic spectrum. We're trying to probe the inflationary period. We're trying to look at dark energy and dark matter. The next wave beyond that is to be able to look at gravity waves, try to understand the ripples in space-time. The LIGO instrument, which I think Scott referenced when he was here a couple of weeks ago, some of you would know more about it than I do. It's active out here. There's a node here in Hanford and one in Louisiana. The creators of that experiment won the 2017 Nobel Prize in Physics because they detected gravity waves from the interaction of two black holes in space. The reason why I'm showing it is that we hope to take the LIGO experiment to space in partnership with Europe in a mission they call LISA, Large Interferometric Space Assembly or something like that. Anyway, it's gonna essentially be 3 LIGO-type nodes, very distant in space, operating as one huge antenna to detect gravity waves. And so that's where we're headed. I don't know when that's going to happen. It's probably at least 10 years away. The throttle is of course dollars, and there's only so many dollars to go around. So what does all this mean? What does all this mean for how we think about the universe and our place in it? Well, I worked for a senior scientist at NASA, in fact, the guy who ran all of NASA's science programs, and he liked to talk about why we're doing this exploration of the universe in these 3 questions. How did we get here? Where are we going? And are we alone? It strikes me, and maybe others, that there's a considerable hubris in thinking that we can answer these great questions with scientific observations. But if you come from a philosophical materialist worldview, that probably resonates with you and makes perfect sense. And there are people, prominent scientists and prominent managers of scientific programs who are just enamored with this idea that we are all made from the material of exploded stars, that we are the products of second generation stars that created heavy elements that then coalesce as a function of gravitational interactions into planetary bodies, and those planetary bodies exhibited heat characteristics that formed clever molecules, not just water, but also amino acids, and eventually proteins, and eventually cells, and eventually animals, and eventually us. And that you could tell this end-to-end story that way. Well, a lot of people don't think that's probably quite adequate. And in fact, the space science program at NASA has backed off of this and now talks in terms of understanding the physics of the cosmos and the origin of stars and planets and galaxies, taking a little bit of the hubris out of the expression of where we're going and how we got here. Still working on this question of are we alone? And so people asked me, somebody asked me last week, did I think there was intelligent life elsewhere in the universe? And I guess my response is, what do you mean elsewhere? I'm not sure it's here yet. But I'm enamored with Arthur C. Clarke's consideration of the problem. Clarke was quite a visionary. And on the one hand, you think about the Earth and the complexity of life and the amazing nature of the human species, in particular in terms of intelligence and so on, and you think, gosh, that's just got to be a one-off event. It's just far too complex, and the probabilities just don't line up to make it happen. And there are those who will say, gosh, look at the expanse of the universe, the millions of galaxies and the billions of stars. How could it possibly be true that we are the only ones? And so Arthur C. Clarke pondered that question, and people asked him what if he thought there was intelligent life elsewhere in the universe, and his response was, I don't know, but either way, the answer is amazing. And I think there's some wisdom in that. when I think about this question, I'm drawn back to Scripture. Psalm 19 was an important one. Another important one for me is Psalm 8. When I consider the heavens, the work of your fingers, the moon and stars, which you have ordained, what is man that thou art mindful of him, and the son of man that you visit him? And this is the question that is, I think, raised in this discussion that Jim and Dan introduced us to through the video series of this idea of non-overlapping magisteria. This idea that there's a realm of science and a set of questions that science can answer, and there's a realm of religion or faith that, and morals, for example, that realm can answer, and that they really do not overlap. They're non-overlapping magisteria. They're tangentially related because I guess humans are thinking about both of them, but they really don't overlap. And Stephen Jay Gould, who created this construct, was inspired to do so after reading the encyclical of Pope Pius XVI, I think it was, who issued a proclamation about essentially accepting a Big Bang cosmology as consistent with the Church's and scriptural revelation. And he wrote this essay about, not essay, an encyclical about why that could be accepted by those of the Catholic faith, and what the limits of that way of thinking were. And it was this idea of the limits of what that thinking was that caught Gould's attention, because the Catholic Church thinks in terms of magisteria. And what it means specifically by magisteria is teaching authority. Who has authority to say, with authority, that something is true or not? And so Pope Pius said that the Church has this magisteria, and it includes things like the historicity of Adam and the nature of original sin, and the doctrine of God and the incarnation of Christ, and all that sort of thing that the Church is normally concerned about. And that other people can go off and do these other things, and we should be thankful for that and participate in that. But there's this magisteria that is the realm of the Church, and by extension of the Pope, who in that construct gets to make those decisions. And so Gould read that, and he, as a self-described person of goodwill, thought, well, here's a way we can collaborate. If we think about dividing up the world's problems, there are those that science can speak to with authority, and those the Church can speak to with authority, and we'll all live happily ever after. That construct has been widely criticized by thinkers across the spectrum. One of whom, for example, was Richard Dawkins, who believes that no, there really is just science. That science has eclipsed religion as a way of knowing, and everything that you want to know about the human person, for example, the human brain, the human mind, the human impulses, can be reduced to chemical interactions and hormone secretion and things that physics and chemistry and biology can tell you about. And all this other religious stuff is just things we in the the pre-scientific mind just imagined, and we live in the echoes of that. But one day we'll all wake up and we'll see that science has eclipsed religion. Well, even those in the philosophical community have found problems fundamentally with Dawkins's notion, and so don't generally. They generally have seen that you can't really do that because, frankly, science, for example, has created problems that it has not yet solved. And so, if you think about where science and religion overlap, I listed 3 items there. You probably know many more, right? There's technology impacts on society and on the environment, right? There are medical ethics questions that are raised by science. For example, should we be doing gene editing of the unborn and that sort of thing? That science can't really answer the question, should we do this or not? It can only answer, can it be done, not should it be done. Military uses of scientific results. There are a lot of scientists who have had crises of conscience, if you will, over having been involved in things like the creation of nuclear weapons and DDT and other things things that science has done that have had some deleterious impacts. And so there's still a recognition, even within the philosophical community, that there are overlapping magisteria, if you will. And in fact, Gould himself recognized that science and religion are not the only players in the game, right? There are actually lots of people who want to tell you the way you should think, right? There are journalists who tell you what you should think. There are politicians who not only tell you what you should think, but want you to then to act on it accordingly. There are scientists. There are authors who try to interpret the world for us and help us understand maybe a perspective we didn't have before. Economics, right? Money talks, right? And money sometimes wants to tell you what to think. Artists want to tell you, share with you at least a different way of looking at the world. Philosophy would like to tell you, if not what to think, at least how to think, and how to think clearly. That there's but that's also has its own challenges. History itself, right? Historians write books all the time to tell us how we should think about how we got to where we are. So there are lots of claimants to magisteria, in my view. There are lots of people claiming to be able to say and speak with authority about a variety of topics. And so in thinking about this, I've just come to the conclusion that Scripture provides a lens through which we can arrive at a properly ordered understanding of the world. And so I've come to view Scripture in many ways, but one way I've come to view it is as a lens through which to understand the world, to understand human interactions, to understand history, philosophy, religion, science, and so on. And I think it provides a valuable service in that realm. And which is why I object to even to the term magisteria. The idea that somebody is claiming teaching authority, right, over some aspect of what I think. I think that's there's something very un-American about that in my view. And so I'd rather take a little bit more humble posture and think about and wish for happily collaborating ministeria, right? Instead of talking about teaching authority, maybe we ought to focus our attention on how we serve society, how we serve the rest of mankind. And many scientists, working scientists, do, right? I think it's only managers of science and writers about science who think in terms of authority. But most working scientists, most working engineers, most working medical people, think in terms of what can I do? How can I make a contribution to the world? And so I'd like us to be able to think in terms of collaborating ministeria as opposed to arguing over magisteria. And I think that that space exploration, both human and robotic, is one of those things that helps us think that way because it, in my view, is so humbling. When you do all of the engineering to program management and training required to send a human into orbit, and then you lose that human, that's a very humbling experience. Similarly, when you point at a telescope and you look across the entire electromagnetic spectrum and you see the wonders of the universe and posit things like dark energy and dark matter to explain phenomena that you don't understand, that's an inherently humbling experience. And so that's one of the reasons why I was grateful to be involved with NASA for as long as I was, because it helps me to think in terms of science and service to society. So I've yacked at you for a long time. I'll stop now. And if any conversation you want to have around this, I'd be happy to entertain. Why what?
Go back to your original question.
Mm-hmm.
Why space exploration?
Why explore? Okay, so that's a great question. Two answers to it. One, in terms of the scientific side, it's really an extension of an enterprise that's been going on for thousands of years, right? The desire to satisfy curiosity, to understand the world of the universe around us. Access to space has just given us a great set of new tools to do that with, to enter into that. In that sense, we're just entering into this millennia-long enterprise of scientific understanding and trying to play our part. Human exploration is a little more complicated. Human exploration has myriad motivations, if you will. They include, in its origin, competition, right? Competition with the Soviets, competition for world attention, competition for a set of ideas, right? Democratic capitalism versus communist tyranny. So that was born out of that competition. But there's also a curiosity element there too, right? How high can human aspirations reach? What are humans capable of accomplishing? Can we do more than we are doing? On the converse of the competition side, there are those who see the benefits of international collaboration in space. The space station, which I showed you earlier, is an international endeavor. It's twice been nominated for a Nobel Peace Prize. One of these days it might make it, because it really did bring, it really has served as a way for us, a subject for us and the Russians, for example, to talk about even in our darker days. You know, even when the Russians walked into Crimea and took that over, there was all this rancor. In the end, much ado about nothing, because we didn't do anything about it. But we could still, through our cooperative partnership with the Russians on space station, have conversation with them, and that was very important. You know, the whole Nixon, if you remember the Nixon-Brezhnev era, the whole détente era was in part enabled by the Apollo-Soyuz mission, the Apollo-Soyuz test flight. It gave us channels to talk to these folks who are our competitors and even our enemies, and gave us a forum in which we could pass messages back and forth and have something else the world could point to give them a little hope. So there's the collaborative part of it. There is the what's sort of nebulously called the leadership and inspiration part of it. There is a whole generation of scientists and engineers in this country who were motivated by the Apollo program. They didn't all work on the Apollo program, but they were motivated by its success to pursue education and careers in science, technology, and mathematics that maybe they wouldn't have otherwise. And so there's that aspect of it. So people don't, as we think about, as NASA, we're called upon to execute the will of the President and the Congress, and we are in this dialogue with them about, okay, why do you want us to do this? And so these are the things that these are the terms in which they speak. They speak in terms of national prestige, of economic competitiveness, of advancing the scientific and technical competency and literacy of the nation. They think in terms of international collaboration. And then there are those outside the agency who are not constrained by being employees of the US government, who will say things like, hey, you know, if we're going to survive, we're going to have to become a multi-planet species. And so the Stephen Hawkings and the what's the guy who's on television all the time? He's almost everywhere. That runs the Hayden Planetarium in New York. Oh heavens! He bills himself the world's sexiest astrophysicist. Oh, who? Thank you. Yes, Neil deGrasse Tyson. Neil deGrasse Tyson is another in his camp. You know, we got to be a multi-planet species if we're gonna hope to make it, because if it isn't, you know, climate change, it's going to be an asteroid impact that takes us out. So we better branch out a little bit. Neil's a great guy. I got to interact with him on the NASA Advisory Council. He's really, I like him a lot, but he's a character. All that to say that there's not one answer to the why question. It's a sort of an ecosystem of whys. And so some people, there are a lot of people who actually object, some mildly, some strenuously, to the fact that the U.S. is investing in human spaceflight, because they feel like there's so many other problems on Earth that we ought to be focused on. And I've had people say that to me, and my response is usually, is that how you live? Right? Do you invest every ounce of your energy and every dollar you have in meeting today's immediate needs, or do you save a little bit? Do you invest in ongoing education? Do you read a book? Right? Why do you do that? Because you want to continue to grow. And NASA, in my view, is that small portion, that less than 0.5% of the federal budget that's invested in thinking about making a better future than we have today. So that's an answer to why. You may not find any of those answers convincing, and that's fine. That's why we have these conversations. There's the because it's there thing, right? That's right. Yeah, right.
To find out what's on the other side.
Yeah, right.
I can make one other comment relative to that.
Please.
From my perspective, that God created it all, and this is our chance to study everything.
Yeah.
And to me, that's the value of what we do and take that perspective. How we choose what we do at any given time, that becomes kind of critical.
Right.
The whole thinking and the knowledge of his creation and trying to understand it and for his guidance to do that, it really is a really exciting place to be.
Yeah, I agree. I mean, it's why those original questions I put up earlier, to me, were so motivating. You know, why are there universal constants? Why do they have the values that they have? Why does the universe behave the way that it does? Does it not scream design at some level? To some people it does, some people it doesn't. But to me, there's something about the joy that comes from pondering the deep things of creation that makes me want to worship. Not a motivation for a lot of people, but it's a motivation for me. So. Anything else?
So what do you think? What do you think about NASA?
That's some pretty phenomenal stuff.
Yeah.
And the fact that phenomenal stuff is possible says a whole lot about the way creation is set up.
It does. It does indeed. It says a lot about the way creation is set up. It says a lot about this idea that what we, I think in the believing community, call being made in the image of God, that there is that echo of the divine in us, that it's amazing that we can come to understand these things, right? It's amazing that somebody could sit down and think of, E equals MC squared. It's amazing that somebody could think of, well, okay, optical telescopes are great, but they can't tell us everything. Let's do one in the infrared and see what that, it's amazing that people can think of that stuff and solve those problems. Yeah, Mark, you said it.
To me, some of the time frames that you have and the stuff that's coming was just shocking. Like in the next couple of years, the things that they're trying to do. And I don't know if that, if the rate of our kind of exploration is accelerating, or if I'm just out of the loop, which is quite probable. But it's like, man, they're developing stuff that's going to go to Mars, in a decade or something, and the Moon in 5 years. I think you said 2024 on one of those. Again, that's just incredible.
Yeah, it's kind of funny because there's some general relativity going on there too, because from where you sit, it looks like, wow, this is all happening fast right in front of us. For those of us who have been inside the thing, it's like, man, this is taking a long time. We should have done this years ago. So I think relativity is true, I guess is what I'm trying to say. Yeah.
50 years.
Yes.
On the moon.
Right.
That's forever.
Right.
And so, yeah, I don't see things happening really fast. And
Yeah.
Things are happening so slow because of congressional spending, congressional approval.
Yeah.
And things that were planned by NASA, to be launched, 12 years ago.
Right.
Have been launched.
Right. The issue is not technology. The issue is political will.
It is.
Right. And not just political will, but vacillation in the political will. Right. Because we've had several stop and start programs in the last 20 years, but for some reason we've gotten into this ethos or lack thereof in U.S. politics, where if it was the last guy's idea, it's got to be terrible. So we got to do something different. And then 4 years later, the last guy's idea, he was terrible. That's why we threw him out. And so we got to go do something different. So we're victims of that as well, which is why my boss has been so cagey in all this, in trying to do the infrastructure items that we're going to need regardless of destination, as far as human spaceflight goes. Where I think, Mark, your observation is right on is on the robotic science side. There have been some quantum leaps, if you will, in understanding. Hubble Space Telescope was a huge milestone, a huge elevator in our understanding, and the launch of Kepler was huge in getting that in terms of advancing our understanding of exoplanets. And so there have been these from historical standards rapid leaps in understanding of the physics of the universe. that has gone on, and I think is accelerating. I think you're going to see another acceleration of it when James Webb is launched. Again, depending on where you are in the expanding universe, things are moving fast or slow.
For me, you summed it up well early in your talk when you said there's the book of the Word, there's the book of the world, and you look at James Webb or Kepler or the Rovers or any of this, it's very easy to say those things glorify the intelligence of man, but they really don't. They're only possible because of I'll run out of adjectives, but the incredible intelligence of our Creator that made all of that possible and made it even possible for us to conceive of doing those things. All of this great advancement glorifies Him and teaches us about Him and should bring us, I think, to our knees in admiration and worship of Him, because it's all understanding Him and what He's done, what He can do and is doing.
Right, and I couldn't agree more. There are a lot of people who don't agree, right? Because they're sitting on the other side of the fence, right? The God of this world has blinded the minds of those who don't believe. And so I view creation, I view the created order as almost like a mirror for self-understanding, right? Am I going to look at a Hubble Space Telescope image and am I going to be prone to worship, or am I going to be disposed to a naturalistic worldview? And
What kind of a mind takes the speed of light and makes it the balancing term between energy and mass?
right,
What kind of a mind could even conceive of such a thing and then do it?
right. You know, it's really interesting to follow the history of ideas, because the folks who thought of those things, you know, the Newtons and the Keplers and the Faradays and even up to Einstein, all viewed this as trying to understand God's creation. Somewhere, you know, post-Darwin, there was a shift in thinking that this could all be an entirely naturalistic process. And I think, again, that's more, that says more about us than it does about the nature of the universe. It's just kind of the way I've come to think about it. Because when you consider these questions, and I put Psalm 8 up there because what is man that thou art mindful of him? Some of you have probably heard this story if you've hung around, listened to lots of sermons over the years. But Harvard School of Philosophy, about getting a new building when you're in an old department in a major university is like a once in a century event. And in the late 19th, early 20th century, Harvard's philosophy department got a new building. And the chairman of the philosophy department decided he would put it to the faculty what saying should go on the top of the building. If there's a word for it, it's on top of the building. But when you walk up to it, what do you see, right? And so the philosophers got together and decided that they would pick a saying from the earliest philosopher, the first of the great Greek philosophers, who said that man is the measure of all things. And so what they wanted engraved over their building was man is the measure of all things. So the chairman of the philosophy department cogitated on that over the summer, and when they all came back in the fall for classes, they were horrified to find that he had written, "What is man that thou art mindful of him?" And so if you go to Harvard today and look at their philosophy building, that's what, because it's a once in a century event to get a new building, that's what's written over the top of the Harvard philosophy building. And it really said, again, it's the natural world reflects back to us the nature of our own soul in some important respects. Okay, as the wise man said, that's twice as much as I know about that subject.
Well, anyway, great. Thanks so much.
Thank you.